can actually solve it with the various boundary conditions. Okay, we will actually try to finish it today, sir. Okay. So now, fins of uniform cross section. Okay. Let us start the recording.
No, sir.
Yeah. Okay. So if you remember the equation, basic equation is d by dx of AC dt by dx minus h by k das by dx into t minus t infinity is equal to 0. So AC is actually the cross-sectional area, right? AC is actually the cross-sectional area, and AS is the surface area for convection, right? Yeah. So that's why we actually stopped in the last class. So here we are actually saying the fin is actually of uniform cross-sectional area. For example, say we are actually going to have a fin like this, circular fin. Obviously, we are actually going to have the base handle. So here we can actually see cross-sectional area is actually it's actually pi by 4 d square, like that it is actually seen, and the surface area, it is equal to perimeter into length, right? If this is actually the length, then it is equal to 2 pi r into L. Okay, we are actually assuming only the surface area which is actually perpendicular to that of the conduction. Okay. Yeah. So that's what we are actually meaning by fins of uniform cross section. So as we said, AC is a constant. Okay, AC is actually constant. So and therefore we can actually see that DAS. Okay, so DAS we can actually see if we are actually assuming a okay, if we are actually assuming an elemental length. Okay. So elemental length of differential element of length say dx, differential element of say dx. What is actually the DAS surface area?
2 pi r dx.
2 pi r dx. Yeah, 2 pi r. Since it is actually going to be the circular one, if it is actually regular, if it is a rectangle or something, we can say perimeter into dx. Very good. Okay. So where P is actually the perimeter for circle, it is going to be 2 pi r. If it is actually a rectangle or something, then W into T, 2 into W plus T. Okay, like this. So it is better to write P into dx. Okay, so that implies DAS by dx is equal to perimeter. Okay, so now we are actually putting everything onto the top. Okay, so therefore we can actually see this equation 36. This is actually 36, right? That's the number we are given. 36 becomes t square t by dx square minus hk by no, hk is actually down only, right? hp by kac, right, into t minus t infinity is equal to 0. Okay, so d square by t square minus hp by kac into t minus t infinity. Okay. So this is actually the basic equation we can actually see. So this is actually very simple differential equation, second order differential equation. Do you know how to solve this? It is having a constant also here. There is actually constant comes into picture, hp by ks into t infinity. Okay. So what all components will be actually there for the solving this second differential equation?
Sir, particular solution and complementary solution, sir.
Complementary solution, very good. So complementary solution as well as a particle integral, if you can find, then you can actually do this. Okay. So there is actually simple method. So what we are actually trying to do is we are actually trying to make it homogeneous. If we are actually going to make it homogeneous, then there is actually no need to find this particular integral. We can directly deal with the complementary function itself, right? So that's what we are actually trying to do. To simplify, what we are actually going to say is we are actually saying t minus t infinity is equal to theta. Okay, we are actually saying t minus t infinity. So there, what is actually d theta by dx? D theta by dx is d by dx of t minus t infinity. Okay. What is d by dx of t infinity? It is 0.
dt by dx.
Yeah, dt by dx it is going to be. Okay, so because dx is actually constant throughout, it is actually not varying with x. Okay, so therefore the equation we can actually simplify to d square theta by dx square minus m square into theta is equal to 0. We are actually saying. Okay, that is where m square is equal to hp by kac. Okay. So now you can see that we have actually reduced our equation to a homogeneous equation, and this m square which is equal to hp by kac, we are actually calling it as m square because this term is actually comes into picture, and this term as well as square root of hp by kac, those things are actually comes into picture now. And also for when you are actually doing this solution, you can actually see that it is actually coming to be square root of 0, right? And you have to find the square root for that. So based on that, you are actually doing it, right? So in that case, in the solution, solution for this, it is going to be hp by kac and all. So every time hp by kac, hp by root of hp by kac, root of hp by kac, it is actually a bit inconvenient. So that's why we are actually calling it as m square now, is the whole thing, and root of hp by kac is actually going to be m. Okay. That's why we are actually calling it as m square. Okay, and this is actually known as fin parameter. Okay, so this is actually known as fin parameter. Okay, and m m is fin parameter. Its unit is actually going to be 1 millimeter. Okay, hp by kg. m is actually the fin parameter, and its unit is actually going to be 1 by meter. So as I said, we can actually find the solution for this. This is linear homogeneous second order ODE. Okay. You can actually find using d square minus m square is equal to 0. So d is equal to square root plus or minus of m, right? If you are actually having a real solutions, what is actually the solution for that? If you remember, there are various conditions, right? If it is actually real solutions, then what we are actually saying is the solution therefore is actually going to be theta x is going to be a into e raised to mx plus b into e raised to minus mx. So that is actually the solution. If you can actually brush up your mathematics courses, and then you can actually see that. Okay. So this is actually one of the simplest form in which we can actually do this. If you weren't actually converting it into theta, then you will actually get then you have to actually find the complementary function as well as the particular integral. So everything together will also give the same thing. Okay. So since we actually converted like this, it is actually going to be easy. So this is actually the solution for the fin. So this is how the temperature variation is actually going to be within the fin. So that you can see it is actually going to be exponential variation. Okay. So whether it is the combined effect, how it is actually going to be, we will actually see by finding the constants a and b. Okay. So, but so in any of the situations, if any of the fins, this is actually going to be the general solution. Okay. But in order to do some analysis, we can actually convert it into the hyperbolic functions also. We know that cos h mx is equal to e raised to mx plus e raised to minus mx divided by 2. And sin h mx, we can actually write e raised to mx minus e raised to minus mx by 2. Okay, so therefore we can also write theta x is equal to c into cos h mx plus d into sin h mx. Okay, so we can call it as 38 a. Okay, so this c and d, they are actually different constants. I think that is a plus b by 2, and d is actually a minus b by 2, something like that it will. Okay, so anyway, so either of these equations we can actually use according to our convenience. So we will actually, yeah, so we will actually see which equation is actually more convenient as to solve and all. But it doesn't matter which equation we are actually solving, we will get the same profile. Okay. Yeah. So now we have our basic equations now. Then what does we actually want now to solve this fully? What else we actually want? Is the solution complete?
Boundary conditions.
Yeah, very good. So we need actually two boundary conditions. Two boundary conditions are actually required. Two boundary conditions are actually required. So one is obviously at x is equal to 0. X is equal to 0. That is base of fin. Okay, or fin base. At the fin base. Okay? Fin base is where it is actually being attached to that of the surface. Okay, so this, okay, so this is actually the base of it, and this is actually the base of it at the x is equal to 0, and this is actually tip of it, tip at x is equal to L, assuming the total length is actually L. Okay, so 0, that is actually base of it. We can actually say t is equal to tb. T is equal to tb. That means theta is equal to theta b is equal to tb minus t infinity. Okay, so that is actually the one boundary condition we have. Using this one boundary condition, we can actually solve either of these constant. Okay, so we need second boundary condition. Second boundary condition is at x is equal to L. That is at fin tip or tip of fin. Tip of fin. Okay. So, but at tip of fin, we can actually have different boundary conditions. Different boundary conditions. Okay. Boundary conditions in the sense, what are the different type of boundary condition we can say? Okay. Not different boundary condition, different type of boundary condition. Can anyone say a boundary condition at the tip? Can anyone suggest a boundary condition at the tip?
Convective
Yeah,
or insulation.
Convective is there, insulation is there. Maybe we can actually call it as prescribed temperature is actually going to be there. We can fix the temperature. Okay. So we can actually say that towards the end, the temperature is same as that of the ambient. That means if the length is actually very low. So likewise, 3-4 conditions we can actually give. Okay. So that's what we are actually going to see now. We are actually going to see different boundary conditions. First one is actually the prescribed boundary condition, prescribed temperature. Prescribed temperature. Okay, prescribed temperature. So there is nothing much to discuss in these things, just the derivations only. Okay, so that I am actually not going to explain much. We can actually write down the derivation. That means at x is equal to L, we are actually saying theta is equal to theta L. Theta at L is equal to theta L. Like at theta is equal to 0, we actually said theta B, right? Likewise, theta at x is equal to L, we are actually calling it as theta L. Okay, so that is actually the second boundary condition we have. So if you actually see, we can actually see that it is easy to solve with the second equation, 38a. Okay, with these boundary conditions, it is easy to solve with this second one. So that's why we are actually going to use that equation for solving this particular boundary condition. Okay. So we are actually saying putting boundary conditions in 38a. Okay, at x is equal to 0. At x is equal to 0, we are actually saying theta 0 is equal to theta b. Okay. If you put into, I will just write that equation. Theta is equal to a into cos h mx plus b into sin h mx. So that was actually the equation. So if you're actually putting 0, cos h mx, cos h 0 is actually 1, sin h 0 is equal to 0 itself. Okay. So therefore, we can actually write theta b is equal to a. Oh no, here it is actually c and d, right? It is actually c and d. C and d. Okay. So theta b is equal to c. So we actually got the first constant, which is actually c. So now we are actually putting the second boundary condition at x is equal to L. Theta L is equal to theta L. If you are actually putting that, you are actually getting theta L is equal to theta B cos h ml plus d into sin h ml. So from here, we will actually get d as theta L minus theta B cos h ml divided by sin h ml. Okay. So now, yeah, we actually got now C as well as D. So now we can actually find the full, write the full equation. Theta x therefore equal to theta b into cos h mx plus d into sin h mx, but d is equal to theta l minus theta b cos h ml divided by sin h ml into sin h mx. So now we are actually going to multiply this numerator, denominator into the other numerators, and we are actually going to trying to simplify the equation. Okay. If you are actually doing that, then you are actually getting theta b cos h mx, right, into sin h mx, sin h ml, and theta l is actually multiplied by over here, theta l into sin h mx minus now this term and this term, theta b into cos h ml sin h mx. Okay, so you can see that first term and second term we can actually combine these two. So it is cos h mx sin h ml plus or minus cos h ml sin h mx. We have the identities etc. with us. So we can actually write theta b sin h m L minus x plus theta L. Here denominator is also there. Sin h ml, that is also there. Okay. From theta L sin h mx divided by sin h ml. Okay. So what is actually more important for us, or what is actually more easy for us to write is theta x by theta b. So that is actually more easy for us to understand, and it is easy for us to plot and out. If you're actually using that, then you are actually going to get, we are actually taking a theta b on both sides. So therefore, it will actually come to be theta L into theta b sin h mx plus sin h m L minus x divided by sin h ml. Okay. So that is actually the temperature profile, we can actually say, for a prescribed temperature. we can actually see at m is equal to L, okay, x is equal to L, we can actually see that this term is actually going to be 0. Okay, this is actually going to be theta L by theta B into sin HML. So sin HML top and bottom are actually going to get cancelled. So we are actually going to get theta x by theta B is equal to theta L by theta. Okay. So putting again back to the equation also gives you the same equation. Yeah. So that is actually the temperature profile within this thing. Okay. Yeah, and therefore you can actually see that it is actually hyperbolic, or we can actually also write in terms of exponential. So it is actually going to be vary along the length. Okay. Yeah. So now what we are actually going to more important is actually going to see how much is actually the heat transfer from the fin. Okay. So more important is heat transfer from fin. Okay. How we can actually find heat transfer from fin? U fin is equal to where this heat transfer is actually going to happen. We are having this fin. Okay. What we are actually trying to see is how much heat is actually being given to fin. Okay. How much heat is actually going to be given to the convective heat transfer. Okay. So therefore, how we can actually write it? U fin is equal to. Can we simply write HA T minus T infinity? Can we simply write it like that? Can we simply write HA T minus T infinity? Just yes or no is actually fine. I just wanted to know whether you can actually hear me. Can you all hear me?
Yes, sir.
Yes, sir.
Yeah. So what do you think? Can we simply write as T HAS T minus T infinity? We cannot write because
So T is changing, sir. We can't write
T
like
is actually changing along the x. So what we can actually write is from 0, x is equal to 0 to L, H as theta into, okay, theta into dx. So that's what you can actually write. So in that case, you have to actually integrate it and you have to actually put 0 to it. Okay. So that is actually a bit involved. Yeah, obviously we can actually do that. There is actually no issue in that. But a simple method is that so whatever the heat is actually going to transfer to the convective, it is actually the heat that is actually being given to the fin at x is equal to 0. Right? So whatever the heat given to the fin or transferred to fin at x is equal to 0, that is actually the heat that is actually being transmitted to the ambient. Okay. So therefore, whatever we actually said over here, that is actually true, but that heat actually comes from at the base. So that means that is actually the heat transmitted to the fin. Okay, that means minus Ka dt by dx at x is equal to 0. So at the base, what is actually the heat transferred by conduction from the base material or from the flat plate or from the surface to the fin? That is actually the heat that is actually being transmitted to the ambient. Okay, so that means heat conducted to the fin at the base is equal to the heat transmitted to the ambient. So we can actually either find heat transfer from the fin by integrating the heat all over, or we can actually find what is actually the heat conducted to the fin at the base. Okay. Yeah. So this one, if you actually do, it is actually going to be a bit easy. Yeah, I'm not going to differentiate it. You can actually simply differentiate it, or yeah, better write the differentiation so there is no confusion. We can actually write d theta by dx. We can actually write it as theta L into m, okay, because m is actually going to come out cos h mx minus theta b m into cos h m L minus x divided by sin h ml. Okay. So now we are actually using at x is equal to 0. At x is equal to 0, d theta by dx, okay, is actually going to be, we have to actually put x is equal to 0. So what we are actually going to get is theta lm, because cos x 0 is equal to 1, theta lm minus theta mb, x is equal to 0 cos lm, cos h theta b m, theta b into m cos h ml divided by sin h ml, sin h ml. Okay. So now you have to actually find yeah. So you have to actually find q of is equal to minus ka k cross section d theta by dx at x is equal to 0. Okay. So that actually gives us theta b into k a into m. M also comes over. We are actually taking the m also common. So you can actually write cos h ml minus theta L by theta B. Okay. So divided by sin h ml. So, but we actually know that m is equal to what? Root of HP by KAC. So, but we are having KAC also over here. We can actually cancel this KAC so that a square root of KAC will actually come in the denominator. So we can actually write root of, in the numerator, root will actually come. Root of HP KAC into theta B into cos h ml minus theta L by theta B. Okay. So divided by sin h ml. So this is actually the total heat transferred from the fin with the prescribed temperature at the end. We can actually call it as this can be actually call it as 40. We can actually call it as 48. Okay. Yeah. So again, we can actually have in some textbooks this root of HP by KC into theta B. It is actually termed as capital M. Capital M into, because that also comes again and again in many of the equations. Cos h ml minus theta L by theta B divided by sin h ml. We can actually call it as a 42. Okay, where m is equal to square root of HP by K HP KAC into theta B. Okay, so for a particular fin with a particular boundary condition as theta B and theta L, so this is what we can actually have. Okay, yeah. So that is actually the heat variation along the length for a prescribed temperature. Okay, and that is also we can actually find this what is actually the heat transfer from the
Excuse me, sir.
yeah, sure.
Sir, are we not considering the convection that takes place at the cross section at x is equal to L in
No,
that cylinder?
there we are actually that is actually the boundary condition.
No, sir. I
That
mean,
is actually the boundary condition.
we are assuming that the convection takes place only on the circumference,
No,
but we also have cross section
no.
at the other end.
No, that no. If when we are actually doing that, then what you have to do is then you have to again calculate what is actually the h etc. It is actually comes into picture. Okay? But that is actually not our concern. So when you are actually saying that T B is actually at some particular temperature, okay. So whatever is actually happening outside, that is actually not our concern. Okay? We cannot actually, we don't know also what is actually outside. It might be actually vacuum. Outside it might be actually going to be very low convective. It might be actually very high convective, etc. Okay, so we don't have to worry about that because once it is actually some temperature or some heat transfer or some boundary condition is actually given. So this is actually what we can actually say. Okay? And obviously, yeah, as you said, if outer condition is actually given and it is actually expressly said that the heat transfer is actually also happening from the tip, then you can actually consider what is actually going to be from the tip. Okay, So unless it is actually not explicitly said, then you don't have to worry about that. Okay? But yeah, very good observation. Okay, very good observation. That is, whatever we actually said is actually from the wall fin, okay, by keeping this temperature as actually constant. We don't know what is actually the outside condition actually. Okay. Yeah.
Yeah,
Very good
fine.
observation. Yeah, very good observation. Yeah. Yeah. So that is actually the one boundary condition, which is actually the prescribed temperature. So now we are actually going to see the next one, which is again a common one, which is actually the convective heat transfer. Convective heat transfer. Now, whatever we actually said, we will actually consider over here. Convective heat transfer. Okay. Yeah. Again, what I'm actually saying is, over here, what we actually said is, we are actually calculated by making into account this heat transfer to the base. Okay, what we actually calculated this by taking into account heat transfer to the base. Okay, so with that base, we are actually saying what are actually the heat transfer and in every direction. Okay, so even if some heat is actually transferring in this condition, so it will be actually automatically taken care of. Okay, yeah, but if that is actually not the case and you are actually calculating with respect to this one, okay, if you are actually calculating with respect to this equation, then whatever we actually said is actually true, but that is actually some additional term that actually comes into it. Okay. So now we are actually going to see the next boundary condition, which is actually the convective heat transfer. Okay. We can actually see at x is equal to L, what we are actually saying is minus k d theta by dx is equal to h into h tip, because we already have actually considered this heat transfer coefficient over here, right? That actually comes into this term m also. So that is actually h, and h tip is actually different, which is actually h tip at the tip. Okay, h tip into theta at x is equal to L. But we don't know what is actually theta at x is equal to L. Our condition is actually h and t infinity. H tip and t infinity is actually our condition. Okay, so now we are actually putting here also we are actually using equation 34a. Okay, so that means that theta x is equal to c into cos h mx plus d into sin h mx. Okay, at x is equal to 0, so it is actually not changing. Okay, at x is equal to 0, we are actually getting theta b is equal to c. So that is actually constant. So now we are actually finding what is actually going to be at x is equal to L. For that, we need to actually find what is actually d theta by dx. So to find d theta by dx, it is going to be equal to Cm, but we actually know as theta b, right? Theta b into m, d by dx of cos h mx is m into sin h mx. In hyperbolic, there is no change in change to minus or plus, etc. Plus d into m cos h mx. Okay, that is actually d theta by dx. So therefore, we can actually say at x is equal to L minus k d theta by dx at x is equal to L is equal to h tip into theta x is equal to L. Okay. Yeah, so if you are actually going to incorporate that, we can actually see that minus k into theta b into m sin h ml plus d into dm dm into cos h ml is equal to h tip into theta L. Theta L means here directly itself to this equation we have to actually put our m L. So tip into theta b cos h ml plus d into sin h ml. Okay. So from here, you can actually see that we are actually going to get d is equal to minus theta b. I'm not going to for the simplification. I'm just saying d is equal to minus theta b into km sin h ml plus h tip into cos h ml divided by h tip sin h ml plus km cos h ml. Okay, so that is actually what we are actually getting for d. So now we have c as well as d. C is actually theta b itself. D is equal to going to be this much big equation. Okay. So putting it back into the equation, what we are actually going to get is theta by theta b is equal to. I'm not going to show an intermediate step. It is very simple only. You have to actually rearrange it. The final equation we can actually write as cos h ml. Okay. So cos h m L minus x cos h m L minus x plus h tip by km into sin h m L minus x divided by cos h ml cos h ml plus h tip by km sin h ml. Okay, so that's what we can actually write for the temperature profile along the length for a convective boundary condition. Okay, yeah. So in this case, obviously, it is actually being considered what is actually the heat transfer from the other side. Okay. So this is actually the temperature variation along the length. Then we need to actually find QF is equal to, as we know, minus KAC d theta by dx at x is equal to 0. At d theta by dx is going to be minus m sin h m into L minus x minus h tip by km into m cos h m L minus x. Okay. So divided by cos h ml plus h tip by km sin h ml. So if you actually put it into the equation, so we are actually going to get QF is equal to KAC m theta b into whatever we are actually going to have it over here. Okay, we can actually write sin h m l, and we are actually putting x is equal to 0. So this is simply theta x. So QF is equal to minus KAC d theta by dx at x is equal to 0. We have to put here, wherever x is actually there, we have to actually put it to 0. Sin h ml plus h tip by km, okay, cos h ml divided by cos h ml plus h tip by km sin h ml. Okay, so that's what is actually the total heat transferred through a fin if it is actually having a convective boundary condition at the end. Okay, so this one also we can actually write as m, because where m is equal to, as we said, root of hp by kc theta b. Okay. So m into whatever it is actually going to be there. We can actually follow it as 42 a also. Okay. Yeah. So that is actually the total heat transferred through the system if you are actually going to have this convective heat transfer condition at its end. Okay, yeah. So these are actually the two conditions whatever we have. So and these are actually yeah. So this Q at the end, convective heat transfer at the end, so that is also very important boundary condition as it is. Okay. So now we are actually going to see the third one. Can you actually see one more conditions? Any condition that actually comes to your mind? We can actually say constant heat flux, right? Constant heat flux condition is actually fine. But more than constant heat flux, what we are actually saying is adiabatic type. Okay, so more constant heat flux at the end, it is actually not that common because constant heat flux at the end, so that is actually somewhat equal to a more appropriate one is actually the convective heat flux. Okay. So, but more than that, what we have is actually an adiabatic tip condition. Okay, adiabatic tip. Okay. So in case the tip is actually going to be adiabatic and therefore it is actually not transferring heat, okay, then we can actually call it as adiabatic tip condition. So this is actually the adiabatic tip. So what we are actually saying is convective heat loss from the tip is negligible. Okay. Convective heat loss from the tip is actually going to be negligible. Okay. So that means if over here the convective heat transfer coefficients are actually very high, right? At the H tip, the heat transfer coefficient is actually very less. For example, H tip is actually going to be much less than that of H. So we can actually consider it as an adiabatic because heat transfer from there is actually going to be negligible compared to the rest. So in that case, what we can actually say is, so that's for the condition is theta by d theta by dx at x is equal to L is equal to 0. That is actually our condition. Okay. So what you have to do is, obviously, you can actually find that using this equation. Okay. From this equation itself, we can actually say from at x is equal to 0, from theta b, we can actually get c is equal to theta b. And then you can actually use again this one. We can actually make it a 0. Okay. We can equate it to 0 and you can actually calculate the okay. So, but easiest method is since we have already calculated what is actually the temperature profile for the convective condition. So now we can actually say is that H tip is actually almost equal to 0. Okay, so that's what we actually said over here, right? So convective heat transfer from the tip is almost going to be 0. So we are actually assuming that because we already have this equation. If you are not having the equation, then you have to actually do it, and it is actually simple only because here we can actually see that instead of h tip here it actually comes as 0. So whatever h tip over here, so that all goes to actually 0. Okay, the same thing only we are actually writing over here. H tip is actually 0, so therefore we can actually take from directly from a 41. 41 is actually the temperature profile for the convective. From 41, you are actually directly getting theta by theta b. Okay, theta x by theta b is equal to cos h m L minus x divided by cos h ml. Cos h ml. Okay, you can call it as 42. Okay, yeah. So this is actually what the adiabatic tip temperature profile is going to be. Okay, so adiabatic tip temperature profile is actually going to be like this. It is actually very simple. Okay, you can actually derive it based on the boundary conditions. So now we know Q of is equal to minus KAC d theta by dx at x is equal to 0. Okay, so you can actually put that directly. You can actually yeah, you can actually differentiate it. You can actually see that minus m cos HML minus x divided by cos HML, and you can actually see that at x is equal to 0, both terms are actually going to be here it is actually going to be sin h ml, and bottom it is actually going to be cos HM. Okay, so therefore you can actually calculate as is equal to m into tan h ml. Okay. to tan h ml. That is actually the total heat transfer. Uh, yeah, that is actually the total heat transfer from a fin with adiabatic tip condition. That means there is actually no heat transfer, convective heat transfer from the surface. So whatever the heat transfer from the surface area, okay, excluding the tip, we can actually see this is actually what we are going to see. Okay, yeah. So that is actually going to be the convective. That is actually going to be the heat transfer from a fin with adiabatic tip condition. We have actually seen a lot of equations till now. So one more condition I am actually going to say, which is actually going to be infinite long. Infinite fin. Infinite fin or infinite long fin, whatever it is. So that means L tends to infinity. So that so this is actually very important for this condition. It is important because there is so much of we will actually see later. There's so much of physics actually comes into picture. This actually gives us an idea on how much should be actually the length of the fin, etc. So this is also an important topic. Okay, as well as the adiabatic also. It is also an important boundary condition, not from a practical point of view, but it actually gives us so much idea of what should be actually the length and what should be actually the best condition, etc. So those things we will actually see later. If you are actually wondering what is actually the need for an adiabatic tip, it is more than a practical use. This is actually more from an academic interest, so that we are actually making something a base for the comparison to see the performance of other fins. Okay? Adiabatic tip as well as infinite fin, they both are actually kind of a baseline so that we can actually see or we can actually compare with other fins. Okay. So here,
Um,
yeah,
so like, is it like from this we will going to find out, okay, what should be the optimum length, because after that
yes,
length there will be no use of it.
yes, yes,
Like
yes, definitely, yeah. So that we will actually see. So based on fin effectiveness and all, we will actually see what should be actually the length. So what does a infinite long means? Whether it is actually 1 kilometer length, can we actually consider as infinite, or can we actually consider 1 centimeter as infinite long? So those things we will actually see. Can what should be actually the proper length also? Yeah. So that's what we are actually going to see. Comparing these two, infinite long and adiabatic fin, we will actually compare these two and we will see what should be actually the optimum length. Yeah. So here, obviously, you can actually use the equation theta is equal to C cos h ml and uh, D sin h ml. But L actually comes infinity, and again, it is actually a bit difficult for us. So, not going for that. So, what we are actually saying is here we are actually using the equation A into e raised to mx plus B into e raised to minus mx. Okay. Just for our convenience, I am saying. Okay. We can actually use this one, and we can actually do that. So first of all, we actually know that as okay, we can actually see that at x is equal to 0, okay, at x is equal to 0, theta b, uh, yeah, so theta b is actually going to be a plus b, okay, so a plus b it is actually going to be, but what happens at x is equal to L? Okay? X is equal to L means we are actually going to have uh, I don't know, maybe it is actually theta L at the end, and we can actually call it as theta L, and it is actually going to be a into e raised to infinity plus 0. It is actually going to be like that. Okay. So therefore, it is actually going to be an confusing over here. Theta L, we are actually saying a into e raised to infinity. Okay. So is that actually physically possible? E raised to infinity means it is actually going to be exploded. It is always also exponential. Is that actually possible that the temperature at the nth is actually going to be infinity? It is
no,
not
sir.
physically
No, sir.
possible. Okay, so the solution is that therefore, okay, so for a bounded solution, we have to actually say that we have to actually say that for a bounded solution, we are actually saying A is equal to 0. Okay? That is actually the only possibility we have, right? So therefore, we can actually say that theta x is equal to A into or B into e raised to minus mx. Okay. So therefore, we can actually see that at x is equal to 0, at x is equal to 0, theta b is equal to b. Okay. So therefore, we can actually see that for an infinite length, theta x by theta b is equal to e raised to minus mx. Okay. So it is actually going to be exponentially reduced. So it is actually going to be 45. So this one with much confidence we can actually draw, okay, how it is actually going to be. So we can actually say theta TB, if it is actually TB, and here we are actually saying that is actually T infinity. At the infinite long, it is obviously going to be equal to, as L tends to infinity, e raised to 0, it is 1 by e raised to infinity, it is actually coming, right? So it is actually going to be 1 and therefore 0. So therefore we can actually say that Tx Tx is actually going to be equal to that of T. T is actually going to be that of T infinity at x is equal to L. So that means at x is equal to L, at x is equal to L, that L tends to infinity, we can see that T tends to T infinity. Okay. So that is actually exponentially approaching. Exponentially, it is actually varying. So that is actually x. Okay. And over here we are having T. Okay. At the base, we are having the maximum temperature, what is actually Tb, and towards that, it is actually exponentially varying. For other fins also, this kind of curve only we are actually going to have. Okay. But we don't know, it is actually a bit difficult to draw from these equations. Once you actually get the values and we are actually plotting it, it might be actually coming something like this or something. Okay. So maybe the slope etc. are actually going to be different. Since the equation is actually going to be very simple in this particular case, we can actually draw it with confidence. That's why I actually draw this temperature profile along the fin only for this infinite long condition. So others also, it will be actually similar to this, but we don't know for sure. Okay, yeah. And in order to find the heat flux, Qf is equal to minus KAC d theta by dx at x is equal to 0. What is that? So it is actually minus m. Okay, minus m e raised to minus mx at x is equal to 0, e raised to minus m0. So that means it is equal to 1. So we can actually say k ac m into theta b. Okay, smaller. So that is equal to capital M. So that is actually the heat transfer. Okay, heat transfer to an infinite long fin. Total heat transferred through the fin from an infinite long fin. Okay. Yeah. So now we have actually seen 4 different conditions, and we have actually seen how the temperature variation is actually going to be, as well as how much is actually the heat flux through each condition. Okay. Yeah. So the important one is actually obviously the prescribed temperature as well as the convective one. Okay. And this adiabatic as well as the long fin, we will actually make it undergo further analysis, so that some idea of the geometry as well as shape of fin and length of the fin etc. comes into our mind. Okay. Yeah. So any doubts in this? Okay, so we can actually stop our class over here. Let me just, yeah. If you have any doubts, we can discuss. Otherwise, we can stop the class. Okay, okay then. Have a nice day to all.
Thank you, sir.
Thank you, sir.
Thank you, sir.